তো আজকে আমরা এই ভিডিওতে স্টিরিওকেমিস্ট্রির বাকি পার্টগুলো ডিসকাস করব। যেটা আমরা শুরু করেছিলাম যে আগের ভিডিওগুলোতে স্টিরিওকেমিস্ট্রি টপিক নিয়ে, যেটা ছিল একটা অর্গানিক কেমিস্ট্রির পার্ট। তো আজকে আমরা বাকি অংশগুলো ডিসকাস করব। প্রথমে আমরা অপটিক্যাল অ্যাক্টিভিটি অফ এ কম্পাউন্ড এর সম্বন্ধে জানব। Compounds may be optically active due to the presence of uh, number 1 chiral center, number 2 chiral axis, number 3 chiral plane, and number 4 helical chirality. It is very important for upcoming CSIR NET and GATE exam. Compound 1 contains chiral axis, that's why it is optically active. Compound 2, that is contains chiral plane, that's why it is also optically active. Next, compound number 3 possesses helical chirality, that's why it is optically active. Hence the correct match is, that is compound 1 possesses the chiral axis, and compound 2 possesses the chiral plane, and compound 3 is helical chirality. So even we draw the structure, then we will understood better because it's organic chemistry, so structure are the important things. So you draw the structure of your notes. Next, compounds can be optically inactive due to by both the internal and external compensation. Internal compensation, this is judged by the presence of symmetry element in the molecule. Cn is not related to the optical activity of a compound, but if any of the rest three symmetry elements like sigma, Sn and I are present in the molecule, then the molecule will become optically inactive. A brief description of the above symmetry elements are given below. Simple axis of symmetry, that is Cn. It is an imaginary axis drawn through the molecule so that if the molecule rotates through an angle of 360 degree by n, another molecule which is indistinguishable from the original one results. A molecule can have more than one type of Cn axis with different values of n. Cn axis with highest value of n is called principal axis. Principal axis optical activity of a compound is independent on whether Cn is present or absent. Example, suppose water molecules contain C2 axis, because if we rotate the water molecule, even center, suppose let the center O atom passing through the O atom, a axis, imagine the axis called principal axis. If we rotate 180 degree, then it's from original state when we started the initial. After that 180 degree rotation, then it will from again the initial position. So it is same things. Plan of symmetry, it is an imaginary plan drawn through the molecule which divided the molecule into two equal halves such that one half is the mirror image of the other half. It can be of three types: horizontal plan of symmetry, vertical plan of symmetry, and diagonal plan of symmetry. Horizontal plan of symmetry, that is called sigma h, vertical plan of symmetry, that is called sigma b, and diagonal plan of symmetry, that is called sigma d. If it is present in a molecule, the molecule will become optically inactive in spite of the chiral center present in the molecule. Example, water molecules also contain a sigma plane, that's called plan of symmetry. Next, center of symmetry, it is a point present within a molecule, such that if a straight line is drawn from any part of the molecule through that point, the extended an equal distance by a straight line on the other side, then a same atom or similar part of the molecule will obtain. If it is present in a molecule, the molecule will become optically inactive in spite of the chiral center present in the molecule. Example, tetrafluoroethene contains I point, that is in center where presence I, that is called center of symmetry. Next, alternating axis of symmetry, that is a molecule is said to have alternating axis of symmetry of n-fold if the molecule is rotated through an angle of 360 degree by n about the axis, followed by reflection in a plane perpendicular to the axis. Result, indistinguishable structure with the original one. Rotation followed by reflection or reflection followed by rotation leads to the same result. If it is present in a molecule, the molecules will become optically inactive in spite of the chiral center present in the molecule. Example, alpha truxylic acid contains S2 axis. Next, external compensation. When a molecule is present as an equal mixture of enantiomers, it is called racemic mixture. It is very important. The racemic mixture is optically inactive due to external compensation. Here the dextrorotation of one enantiomer is compensated by the levorotation of the other enantiomer. That is called DL pair, dextrorotatory and levorotatory. Next, RS nomenclature. First, assign the priority of a groups 1, 2, 3 and 4 of the basis of CIP rule. CIP means scan, Ingold and Freelock. CIP rule, that is, higher is the atomic number of the directly attached atom, higher will be its priority. So if the fourth group is at vertical position, then 1 to 3 clockwise rotation is called R. Even 1 to 3 anti-clockwise, then rotation is called S. Next, highlights the point, if a fourth group is the horizontal position, then 1 to 3 clockwise rotation is S and 1 to 3 anti-clockwise rotation is R. It is very important for find out the any molecule configuration. So that's why we can use the CIP rule. Next, conformational isomerism. That is, a molecule can have two conformational isomers. One is eclipsed, another is staggered. Also, eclipsed conformers is subdivided into two forms. One is fully eclipsed and another is partly eclipsed. Similarly, staggered conformer is subdivided into two forms, A gauge form and B antiform. The four conformers in case of butane, that is C2C3 bond rotation, is shown below. That is partly eclipsed and fully eclipsed. We know that the Gauss butane interaction, steric crowding, etc., the fundamental factor of organic chemistry. Next, antiform and Gauss form. Next, stability of conformers. General cases, as fully eclipsed conformer involves high steric repulsion between the two bulky methyl groups, it is least stable due to interaction between them. Then partly eclipsed conformer is also destabilized by the one bulky methyl and one smaller hydrogen atom. Hence, it is a somewhat more stable than the fully eclipsed conformer. Gauge conformer contains the two bulky methyl groups at an angle of 60 degree. Hence, it will have much less steric repulsion between the bulky methyl groups. Hence, it is much more stable than the both fully and partly eclipsed conformers. Finally, in case of anticonformer, the two bulky methyl groups are 180 degree apart from each other. Hence, it involves least steric repulsion between the bulky methyl groups, making it more stable. The anticonformer, this is due to the following reasons: the formation of intramolecular hydrogen bonding, as for example ethylene glycol or 1,2-diol. Next, hyperconjugation, that is 1,2-difluoroethane, and electrostatic interaction, 1-bromopropane.